Hello everyone and welcome to Network Labs. Today in this video, I will show how to configure and enable MPLS traffic engineering in a service provider network. In this video, we will use Cisco IOS XE and ISIS for the IGP protocol. MPLS will also be enabled within the network and pure IP protocol to the customers. For ISIS, all IGP traffic must traverse through one router, which is P7. To do this, increase the metric on all links except the link facing P7. In this lab, we will enable MPLS TE support on all routers and links within the ISP. Configure dynamic primary MPLS tunnel between PE1 and PE4. Configure explicit backup MPLS tunnel between PE1 and PE4. Enable and configure FRR for fast convergence. Loopback and interface addresses are pre-configured on all the routers to save time. Let us begin the configuration by setting up the IGP, which is ISIS. Enable authentication using a keychain for ISIS and MD5 as the authentication mode. Use the net address value on the screen. All routers must be in level 1 only. Activate all the links within the ISP, including the loopback interface, and set the network type to point-to-point. Traffic should flow through the P7 router. Let us start with PE1. First, create a keychain and set the string and authentication mode. Next, configure ISIS process with a tag value. Under ISIS, configure the net address. Then, the type and level, followed by the authentication mode. Next, bind the keychain. Then change the metric style to wide. Make sure to enable ISIS on the loopback 0 as set it to passive. Then, activate ISIS per interface. Under each interface, bind the ISIS process. Then set the level and network type. And the metric value if required. That is all for the IGP configuration. To save time, copy and paste the script in each router. Also, enable ISIS between PE1 and CE1, then PE4 and CE2 for end-to-end connectivity. IGP configuration is done. Let us check the connectivity in each router before we proceed on the next step. As checked, all the PE routers has a view on the whole topology and the traffic traverse via P7 primarily. Ping from CE1 to CE2 is also successful. Let us proceed with MPLS LDP configuration within the ISP. MPLS LDP is optional in MPLS TE implementation, but we will configure it for other traffic not requiring traffic engineering. We will start with the basic MPLS configuration. Next is LDP authentication, followed by LDP session, protection configuration. Next, MPLS TTL disable configuration. Then MPLS LDP label filtering configuration. And MPLS LDP synchronization configuration. For the basic configuration, set the loopback 0 as the router ID. Then, set the protocol to LDP. Then set the label range where X is the router number. Configure MPLS LDP auto-config under ISIS process. For LDP authentication, require a password. Then set the password for fallback. For LDP session protection, configure an access list permitting only the loopback 0 network. Then enable LDP session protection globally for the access list created. Next, disable TTL propagation to hide the PE router's labels. For MPLS LDP label filtering, create a prefix list permitting only the loopback 0 of the MPLS routers. Enter MPLS LDP label configuration, then bind the prefix list created. Lastly, under ISIS process, configure LDP synchronization. To save time, copy and paste the script on all the MPLS routers. In PE1, make sure to disable MPLS facing the customer. In PE4, disable MPLS facing CE2 also. Let us check the forwarding table and LDP neighborship status of each router. In CE1, let us conduct a trace route going to CE2 to verify the LSP path. In CE1, the MPLS router's labels are hidden since we have disabled the propagate TTL forwarded. End-to-end connectivity between CE1 and CE2 is still successful with the same path. Now let us continue and proceed with our main task, which is to enable and configure MPLS TE and tunnels within the network to achieve the requirements. Take a look on the diagram. By creating MPLS tunnels, we can dynamically or explicitly set a tunnel to cater traffic based on the bandwidth or traffic priority, and the other links to regular traffic using the IGP. With MPLS TE, we can define how traffic flows through an MPLS core network. We can steer traffic to maximize the efficient use of available bandwidth between routers. Unlike in IP routing, the traffic is only manipulated with the use of cost or metric. Let us continue with the configuration. First, enable MPLS TE globally on all the routers. Then, enable and configure MPLS TE on all the interfaces within the network. Next, enable RSVP to support reservation. Globally, enter the IGP process and enable MPLS TE. Globally, configure MPLS traffic engineering tunnels using this command. Then, enter all the interfaces within the network and apply this command. Followed by enabling RSVP bandwidth reservation. For now, we will not configure any bandwidth reservation value and just use the default maximum reservation, which is 75% of the link capacity. Under the ISIS process, enable MPLS TE by indicating the level. Then, use the loopback 0 as the MPLS TE router ID. And configure metric style wide. Before we proceed, let me show you the default status if we issue the command, show MPLS interfaces. For now, only MPLS LDP is activated. Copy the configuration and apply to all the routers and interfaces. Upon MPLS TE configuration, we can see that tunnel status is now up on all the interfaces. Continue the configuration on the remaining routers. Let us verify if RSVP is enabled on each interface. Issue the command, show IP RSVP interface. It is enabled and with default bandwidth reservation. We are done with MPLS TE configuration on all the routers and interfaces. Next is MPLS TE tunnel configuration based on the requirements. First is dynamic MPLS TE tunnel between PE1 and PE4. For this task, in PE1, create an interface tunnel followed by interface number globally. Assign the loopback 0 of PE1 as the source address of the tunnel. Set the tunnel mode, which is MPLS Traffic Engineering. Assign PE4's loopback 0 as the destination IP address of the tunnel. Set the path option to dynamic. And explicitly route the traffic in the tunnel. MPLS TE tunnel is unidirectional. We need to create a tunnel both in PE1 and PE4 for the forward and reverse direction. Let us start in PE1. Copy and paste the script on both PE1 and PE4. We are done with the tunnel configurations on both PE1 and PE4. Let us conduct basic verifications using the commands in the screen on both PE1 and PE4. First, verify the RSVP session details. RSVP status on both PE routers are good. Next, verify the status of MPLS TE tunnel interface in each router. In PE1, the tunnel is up and operational with complete hop list or explicit path. The same status in PE4. Next, verify the routing table to the remote PE and customer if the traffic is routed to the created tunnel. Both the traffic to the remote sites are routed via the tunnel interface on both PE routers. Next, verify that traffic towards CE1 and CE2 is switched via the tunnel on PE1 and PE4. Both traffic is via the tunnel interface with their own label. We can now perform end-to-end testing on CE1 and CE2 towards each other. Before we proceed, let us enable the TTL propagate in PE1, P7, and PE4 so we can confirm the label on the path. Conduct a trace route in CE1 towards CE2. Connectivity is successful, and the path traverse via the tunnel based on the label. Shut down the tunnel interface in PE1 and check the path again. The traffic reverted back to the normal IGP path. The same status in CE2. Dynamic MPLS tunnels configuration in PE1 and PE4 are done. Now let us configure an explicit path from PE1 to PE4 and vice versa based on the diagram. For the configuration, we will be creating an explicit path on both PE routers. Then, manually set the next addresses, which are the loopback 0 IP address in each router on the desired path. Here, the path will be PE1, PE2, P7, PE3, and PE4. That is for PE1. In PE4, the desired path is PE4, PE3, P7, PE2, and PE1. The traffic direction must be symmetric. Next, create another tunnel and apply the explicit path created. The other values are the same with the first tunnel created. Copy and paste the configuration in PE1. The new or backup tunnel is now up and operational. The hop list is the path that we have included in the explicit path created. Here, by creating an explicit path, the path is not taking the IGP cost anymore, unlike in dynamic path. Go the PE4. Then configure an explicit path and new tunnel. Edit the next address for the explicit path. Copy and paste the configuration to PE4. The new tunnel is now up and operational. And the hop list matches the IP addresses in the explicit path. Let us conduct basic verifications in PE1 and PE4 before we proceed with the connectivity in CE1 and CE2. As we can see, the best path is via Tunnel 2. To make Tunnel 1 the primary path, add an absolute metric with lower value than in Tunnel 2. Then higher absolute metric in Tunnel 2. Add the configuration on both PE1 and PE4. Now let us verify the routing table again. The primary path is now Tunnel 1. To check if Tunnel 2 is working, shut down Tunnel 1. The best path is now Tunnel 2. Both the routing and forwarding tables of PE1 and PE4 towards the customers now chooses Tunnel 2. Go to CE1 and conduct a trace route to CE2. The traffic successfully flows via Tunnel 2, which is the backup tunnel. Enable Tunnel 1 in PE1 and make sure that the traffic will revert. Both the primary and backup tunnels are now working. Let us proceed on the next task, which is to configure Fast Reroute. I hope that this is informative to you, and thank you for watching.